My name is Daniel Marbach. You can reach out to me if you have any questions on Twitter or X, it's called these days, I believe, but I'm holding on to the icon. That's why I have it. I refuse to call it X. So you can reach out to me there on the Daniel Marbach, and you can also send me emails. I also have business cards over there if you have any questions, should I not have time to answer any questions during the talk. So I'm the kind of person, I call myself a practical learner. I don't know if that's an official term, but one of the problems that I have is when I'm reading a book about, for example, performance optimizations, because I had this dream, I wanted to become better in understanding performance optimizations and the context of my code, how I can make the code faster. And I was reading books, I was watching talks online, and then I was like, yeah, now I got it figured out. And then I was sitting in front of my code, and I was like, how did that work again? I wasn't sure, and then I usually go through a series of sort of trial and errors and tears and sweat, and at some point I really got it figured out, but I can't just read a book and then I have it sort of in my memories. And one of the things that I usually do when I'm learning something, I'm trying to find something practical I can apply. And I was looking, I was like, oh, okay, there are open source projects out there that probably maybe need a hand to help out. So I was looking around, I found the Azure .NET SDK, which is a pretty large repository. I started making contributions to it, trying to apply my learnings. And lo and behold, I'm now probably around 90 pull requests against the Azure Service Bus.NET SDK. And some people have called out that I probably have done more pull requests against the SDK than some other internal Microsoft employees. I'm not sure if that's true, but it's an honor that someone said that. But anyway, what I wanted to basically condense into this talk is sort of the experience that I got from doing performance optimizations with that repository, so that you can sort of get the gist out of that, and then you don't have to go through tears and sweat like I had to do. Good, let's get started. So what I want to get across here, so this talk is not going to be about sort of horizontal or vertical scaling. It's also not going to be about tools like benchmark.net. I will show some stuff with benchmark.net, but it's not going to be about those tools. It's also not going to be about sort of memory and performance profiling, because that would be a whole other talk, so I'm not going to cover that. So this talk is really about sort of performance optimizations you can apply to your C# and .NET code so that your code gets faster, where it really matters on the hot path. And some people ask me and said, well, but why would you do that with C#.NET? Just use C++ or something like that, because those are, or Rust, because those are truly high-performance languages. And I truly believe that the .NET runtime, including C# and also, of course, other languages that are running on the .NET runtime, have become good languages, and also the stack, the runtime, has become extremely good over the last few years to be a high-performance platform. And there are many, many large-scale projects that are running on .NET. For example, Bing is also running on .NET, right? And maybe you have also read that Bing recently, when they migrated to newer .NET versions, they had like huge improvements in terms of cloud expenditure that they got all reduced. So I believe that .NET is a really good platform to write high-performance code upon it. And as a matter of fact, one of the things that, for example, even the C# team did, right? There's the thread pool. And the thread pool was a highly complicated sort of monster between sort of unmanaged code and managed code. And at some point, the team basically decided to rewrite the thread pool and lifted it up into managed land. And the performance of the thread pool that is now entirely in the managed land is at least on par with the other version, or in some cases even better, right? And now they have sort of a single language that the thread pool is written in, and that's also from a maintainability standpoint is much better, right? So I believe that C++ is less and less needed these days to achieve code that sort of scales really well. But then, when I do these types of performance optimizations, I sometimes hear from my colleagues and peers, wow, but Daniel, this is really crazy. Isn't that premature optimizations? This is highly esoteric stuff. Why would we even bother, right? So, well, I must say that some of the optimizations that I'm going to show you today, they can be called out as esoteric, but I'm going to give you lots of context why I think they are not. And what's really important to me is, don't blindly jump to conclusions and take what I'm showing you today and go to your project and say, oh, I'm going to apply this everywhere. Because that wouldn't make sense, because you would be wasting your employer's time, your own time, and also your customer's time if you do that, right? So what's important to me to give away as a message is the types of optimizations that I'm going to show you today, it is only relevant when you actually have code that is sort of on the hot path, that is executed thousands and thousands of times a second, right? And I'm going to talk a little bit more about that. One of the things that I've also seen for myself is that those performance optimizations, once you start to grasp it, you start to see it everywhere, and it gets really addictive, right? And you start like hacking your code and changing it everywhere. And I must say that I'm the kind of person that sometimes I go really wild. I do lots of optimizations, and at some point I had to sort of apply a hack so that I'm switching off the internet at midnight, because what I'm doing then is I'm not going into sort of past midnight and coding all night long, because I need to sort of stop myself from doing that. So hopefully I'm giving you enough context so that you're not falling into these pitfalls, and you don't have to apply hacks like that to switch off the internet at midnight. So when code is executed at scale, then sort of the performance characteristics of the code really matters. And code that is executed at scale, it should be highly efficient in terms of resource usage, execution time, throughput, and memory usage. Okay, but let's discover a little bit what it actually means. And I have here a sort of a quote from David Fowler. He had a really excellent talk about at scale implementation details matter. And scale for an application can mean the number of users that will concurrently connect to the application at any given time, the amount of input to process, or the number of times data needs to be processed. And for me, the last part is the most important part. For us as engineers, it means we have to know what to ignore and knowing what to pay close attention to, right? And what it means is, essentially, when I go to a code base, I usually assume that the people that have written this code base, they were smart, and they made a bunch of assumptions, and they had to make trade-offs, right? Sometimes these sort of assumptions and trade-offs, they're written down. If we're lucky, we have architecture records or decision records, and then we can grab them, or maybe it's a comment in the source code, right? But sometimes they're not written down, and we sort of have to go and understand, well, what were the people thinking, right? Because maybe someone said, well, it's only going to be executed 10 times a second, right? And then suddenly the project grows, we get more customers, and then it's executed 100 times, 1,000 times a second, right? So what might have not mattered in the past suddenly matters over sort of the time of the project. And we need to sort of go and think about, well, have people assumed that this is only going to do a new once a day or whatnot, right? And sort of when we have code that is executed thousands of times a second, all these assumptions start to matter, because allocations will essentially affect the memory throughput. It will also slow down your code, right? Also, CPU algorithmic complexity will also start to matter on the code that is executed at scale. So what I've done is I've also tried to sort of condense the things that I learned into the two most important rules. And I want to present them here so that you can take it away. And should you be already a little bit tired because it's already late today, right? Then these are the two most important rules that you should take away from this talk, and then you can fall asleep. Hopefully you're not falling asleep, but I'm just saying. So avoid excessive allocations to reduce the GC overhead, and GC is the garbage collection overhead, and avoid unnecessary copying of memory. So these are the two handy rules that you should remember, and if you follow those, then, and you're trying to look out for those things, then you're going to be mostly fine. And the first rule under the category avoid excessive allocations to reduce the GC overhead is think at least twice before using LINQ or unnecessary enumerations on the hot path. So don't get me wrong, I'm a huge fan of LINQ, right? So LINQ is an amazing language feature, it's highly productive, and as a matter of fact, the first version of my code, I'm always using LINQ, even if it's on the hot path, because it's so easy, it's so natural to me, right? And I don't want to miss this language feature, and I'm not going to say to you, never use LINQ, right? Apply it where it's useful. So for example, if the code is only executed once a day or something like that, then use LINQ, right? But if the code is executed hundreds, thousands of times a second, then do not use LINQ, because it's going to sort of slow down the code, because it has hidden allocations that you don't see when you're writing the code, and it's very hard for the JIT, that's a just-in-time compiler, to sort of optimize it. And I know there might be some people in here that are thinking, yeah, but Daniel, I've read all the blog posts that the .NET team has recently published, and there are a bunch of optimizations that they're applying to the LINQ versions as well, and that's absolutely true. So the things that I'm going to show you today, some of these things might no longer be true true maybe 2, 3, 4 years down the line, right? Because LINQ gets optimized more and more and more. For example, also with .NET 8, there are also another bunch of optimizations that are coming out that will also make LINQ faster. But still, or to summarize it, on this blog post, it's actually Stephen Tove's blog post, which is almost a book, right, that they recently published about the RC version of .NET. They're saying, of course, sometimes the most efficient use of LINQ is simply not using it, right? And they added a bunch of analyzers as well that helps to sort of find out where you should not be using LINQ and also do some other means of it. But I just want to say LINQ is great when it's applied in the right context. Cool, let's have a look at a piece of code. Here I have the AMQP receiver. So AMQP is an advanced message queuing protocol, and the Azure.NET SDK uses it for Azure Service Bus and Event Hubs. And it's basically sort of a TCP/IP communication protocol where they're sort of doing handshaking with Azure Service Bus and, for example, in Event Hubs. And this is the sort of the core infrastructure logic that sort of does, for example, acknowledge messages. And here, what we're seeing here is the Azure SDK has a bunch of design guidelines. And one of the design guidelines is forever when you're getting sort of enumerables in, you have to use the broadest possible enumeration type, which is IEnumerable. And here we're getting an IEnumerable of lock tokens. And for those who have never heard that term, lock token is basically sort of almost like it's a GUID, it's a glorified GUID that sort of you are going to use when you receive a message from Azure Service Bus. You're going to have sort of that GUID, and then once you're done handling that message, you send it back to the server and saying, hey, I'm done handling this message, and then it will be acknowledged. And this is how the code looked like. So we got the broadest possible enumeration type in, and then it does a select. It then turns those strings into GUIDs. It does a toArray, and then what it does, it has an if statement where it sort of does a link any, right? It checks whether it has already seen this GUID in sort of an internal in-memory thing, and then once it has done that, it essentially decides, well, if I have already seen it, I go on one path, or I go on the other code path. And now, if you want to understand what this code is actually doing, is we have to sort of look at how this code is going to be lowered. Lowered is just a fancy way of basically saying, well, there's some compiler trickery happening, right? That takes sort of the high-level C# and puts it into sort of the underlying C# that is the most basic one. And if we decompile this code, what we're going to see is that the code looks like this. And I know this is probably a little bit overwhelming, so let me sort of zoom in. What we can see here is that we have this enumerable.any, and then hopefully I can actually show it to you here. No, it doesn't work. Okay, you can see that c.9__2_0 question mark and then equals new func. So what we're seeing here is in this specific code, we're actually having sort of a statically cached delegate. And whenever we are seeing sort of this pattern of C9___ question mark equals, what it means, we're usually in the safe zone. We don't really have to worry about it. So this code is fine. But if we are going and look over here, what we can see is we have a new func of GUID of bool allocation that sort of points to complete internal async method, right? And this allocation is totally unnecessary. And we can get rid of it. How can we do that? Well, it's actually pretty simple, right? We can basically just take the for each, and we can, or the any, and we take it in, turn it into for each, and then we loop through the things, and then we look whether it was already contained. If it was, we go on one code path, otherwise we go on the other code path. So we are still structurally, semantically exactly doing the same, but we're no longer using LINQ any. Now, when we have done that, and we decompile it, we get this. So now we can see here, while we have now a while loop, but that doesn't really matter, we have now this sort of safe pattern that I talked about. We have this C.9__2_0 question mark equals, right? So now we have a statically cached delegate, and now we have no longer an allocation, and now the code is going to get faster. And we are hopefully fine. And now the question is, well, what does hopefully fine mean? How can we be not just hopeful, but actually know that we're doing fine? Well, one way of doing it is we have to measure it, right? Because whenever we're doing performance optimizations, it's super, super crucial to actually not just assume it's going to be faster, because we want to know that it's going to be faster. Otherwise, we don't have to sort of increase the complexity of the code, right? Because we're not achieving anything other than increasing the complexity. And we can do that, for example, with a tool like benchmark.net. And I have here run with benchmark.net sort of the before example with the any against the one version with the for each, and I'm presenting here you the result. I know it's a huge table, don't worry too much. I'm going to summarize it for you. So with that sort of small change, we essentially got the upper level is a throughput improvement of 20 to 40% more throughput, and we got a garbage collection, Gen 0 garbage collection reduction by 20 to 40%. Right? Just by getting rid of the any, we got almost double more throughput, right? And we got lots of Gen 0 garbage collection improvements. But that's super nice with a small change. Now, the question is, can we do even better? And yes, we can even do better, right? Because the ones that were paying attention saw that there was still a select statement in the code, right? Because I only optimized the any. And you might be thinking, yeah, but Daniel, you have to be getting rid of this as well, and we can do that. And I have a bunch of rules that I'm going to show you here. So the first one is, whenever you sort of representing empty arrays, use array.empty, because it's a statically cached empty array, and then you don't have an allocation. The next one is, when you have empty enumerables, use enumerable.empty sort of to represent empty enumerables, again, because it's statically cached, right, for every t, so that you don't have allocations anymore. If you're using C#12, you're already on the new stack. What you can also do is you can now use the new awesome C#12 collection expressions that you can write, and then sort of the compiler understands whether you're mutating the empty array or not, and if it's not mutated on the code path, it actually automatically propagates it for you to an empty array, which is super, super nifty, right? I do prefer personally to be more explicit in my code instead of relying on magic, but your mileage may vary, and I want to let you know that this is a possibility, okay? Then the next one is something that most people forget, right? Collections, when you initialize collections, they have a sort of set of buckets associated with it, right? And then that means it has a capacity. And when you start adding more elements, then it has capacity. What it essentially has to do, it has to grow its capacity. And that usually happens in sort of a twofold sort of way, right? And that growing capacity means it has to sort of allocate more memory, and then it has to reshuffle its internal buckets. So when you know how many things you're going to add to collections, if you know that, you should make sure that you initialize the collection type with the dedicated count that you know you're going to insert, and then everything is also going to be much faster. And then this is a little bit counterintuitive, the last one. This one, use concrete collection types, because most of the time I hear people saying, yeah, but I always want to use IEnumerable or IRead-only connection, the interfaces. I don't like using directly the list or the array. It goes against my ethos of writing code, I don't know what. But for performance-sensitive code, you should actually using the concrete collection types. Because then what's going to happen is in the majority, in all the cases, you're actually getting the enumerator that is a struct, and you're not getting to boxing cases. By the way, this one is also something that gets optimized more and more. So with new versions of the JIT and also with dynamic PGO, you're getting sort of more analysis in your ID, in your code, and then it essentially, when the code is sort of JITted and everything, then some of these cases, they're not, even if you're using a IRead-only collection, it can actually discover that you're using an array or a list, and then it makes sure the code is written in an optimized way. But still, if you really want to make sure that you don't have sort of that boxing of the enumerator, then use the concrete collection types. And then when you have to sort of instantiate collections with sort of the right size, right, you have to know how much you're going to insert, right? And then sometimes you have to do some sort of counting. And the most intuitive version is to use LINQ count, right? But that's not really cool, because then it has to sort of iterate, it has to materialize the collection. And what you can do is, if you're using a version that doesn't have the enumerable.try get non-enumerated count, and try get non-enumerated count, what a mouthful, is basically a method that sort of gives you the count if it's a collection that provides you a count, even if you have an IEnumerable, without actually enumerating and looping through the collection, right? Because that's super efficient, because otherwise it has to go through the whole collection. But what you can also do is if you don't have that because you're on a .NET version that is a little bit earlier, you can use, for example, pattern matching to sort of check whether the collection is of a collection type that has a count, and then you get the count to sort of initialize another collection, and then it's already sort of materialized with the number of buckets, and then you can insert it in a faster way. And then when you're writing high-performance code, one of the things is if you need collections, then make sure you're only instantiating collections when you really need them. If you don't need them, for example, if you have boundary conditions in your code, where you, for example, check, well, if this condition is true, then I'm just going to return, and I don't need the collection, then don't initialize it, right? So sort of restructure your code to only instantiate it when you really need it. And then the last ones, there be dragons, but I'm going to mention it for completeness reasons, is what you can do is when you're accessing collections, there is this, for safety, precautions measurements, there is sort of these boundary checks, right? That you're not sort of going outside the boundaries of a collection. And you can sort of avoid these bound checks by sort of using the unsafe or align the access to the collections. And there are a bunch of helper methods now in the .NET runtime, like collection marshalling or memory marshal or unsafe in the system runtime compiler services namespace that help you to sort of get direct access to the underlying data structure of a collection type. Okay, this is super evil, right? You can squeeze out more performance out of your code if you want to, if you have to, but it's super, super dangerous because then you're sort of outside the safety checks of the .NET runtime, and again, there be dragons, right? Okay. And last but not least, keep yourself up to date with the latest performance improvements, right? Because read those blog posts, because then you're also evolving your understanding of performance improvements over time. Cool. Then let's have a look how this looks like. So again, we had this select statement in there with new GUID and then toArray. So now if we apply all those rules, what we can do is, and I'm showing here the version with pattern matching, because at the time, so we're on Net Standard 2.0 on the Azure .NET SDK, and we didn't have latest C# support, and we don't have the try get non-enumerated count, so we had to apply pattern matching. And what we did there is, even though there is IEnumerable of strings coming in, so the team basically had sort of telemetry of how this method is mostly going to be used. And what we did there is we were sort of saying, okay, in the majority of the cases, we're actually getting materialized collections that are passed into that method. So we're getting arrays, lists, and stuff like that. Only in, for example, unit testing cases, people are actually passing lazy enumerated enumerables. So we can do that, and we can essentially do a type check to see, is the collection that is passed in of type iRead-only collection, because then we have the count. And then we can pass that to the method. And now you might be saying, but Daniel, you just told me that I should always be using the concrete collection types, right? And now you're not applying your own rule. Why are you doing that, you cheeky bastard, right? Well, I must say that like everything in software development, there are trade-offs, right? And in this specific case, because they have these rules that you always have to accept from sort of the customer code, the broadest possible enumeration type, we can't just blindly break the public APIs, right? So we have to sort of play with the boundary conditions that are given, right? So I have to pass a read-only collection of string here. Okay, and then what I'm doing is basically I'm doing a quick check, right? Whether essentially the count is 0. If the count is 0, I can directly use array.empty. Otherwise, I'm allocating an array with the number of buckets, and then I can just sort of new up the GUID and add it there. And now I have way more complex code, right? But now the question is, did it actually help anything? And let's have a look. Again, we have to measure it. And when we benchmark it, and here I'm showing on the screen the first optimized version. That's after version 1. The first optimized version, as a quick reminder, was still using the select statement with a toArray, and was only getting rid of the any call, right? And compared to the more complex, no longer using LINQ-based version. And I executed it again against a bunch of sort of collection types like enumerable, arrays, and hash set. And what we can see here is we're getting, on top of the previous improvements, we're getting 5 to 64% additional improvements, and we're getting 23 to 61% garbage collections reduction as well. Now we can say, cool, we can switch off the internet and go to bed and be happy campers, right? Well, can we? Well, we have to look very closely. If you look very closely, what we can see is in some cases, we're actually slower. We are 56% slower. And those are the cases where we're getting non-materialized collection. When someone gives us an IEnumerable that first has to be iterated through in order to even know what's in there, in those cases, the first optimized version that just got rid of the any is actually the better version, right? And now is the question, should we not do this type of optimization? And here again, the context of the code comes into play. Because the team had telemetry, and we knew only in unit testing cases, we're actually getting sort of lazy enumerated enumerables, and in the sort of the production case, we're always getting, or essentially materialized collections, we can apply sort of the full LINQ, no longer LINQ version, and then we're actually faster, right? Because we have sort of excluded sort of the boundary case of this optimized code where we are essentially getting lazy enumerated enumerables. But if that's not the case, then I would say use the version that you feel most comfortable with, right? Because when you're saying, well, we removed the any, and now we know that we're actually much better than before, right? But we want to leave the select to array because we know we're going to be mostly in the cases of the lazy enumerated enumerables, then leave it as is, right? Because you have to sort of make the trade-offs and understand the code. And what's also important is it's quite likely that you probably have other positions in your code base that have much more sort of impact when you're going to change that, instead of sort of trying to gold plate every piece of the code base that you're working with, right? So what I want to give you away is, again, think and discuss it with your teams about how far should we go in terms of sort of sacrificing readability, increasing the complexity of the code base, right, for the sake of squeezing the last bits out of it, versus just leaving the more simple version, right? And again, the hot path is, we need to think about the hot path. And what's also important, fire up your favorite sort of memory and performance profiler to actually inspect the code at runtime to see what's actually going on, and to also sort of, even if you use, for example, a tool like benchmark.net, then make sure that once you have sort of measured it in sort of this sort of environment where everything is sort of not user executed, then put it into your production system and actually attach a profiler to see if actually if it gives you sort of the performance improvements in the larger context that you are looking for. And like with everything in software, it's sort of crucial to understand how far we should go and when we should stop and focus on our attention on other parts of the piece of the code. Cool. Then let's look at the other one. Be aware of closure and allocations. So I already touched a little bit about closure allocations during the LINQ performance optimization slides that I talked here, but closures can essentially occur anywhere where you have sort of delegates, lambdas, so action and function delegates. When they're invoked, that access stayed outside of the lambda. And what does that mean, right? Let's do a quick example here. So the Azure SDK has sort of this poly retry capability, and it's actually a very simple while loop. So every method, for example, in the Azure Service Bus SDK that is talking to the Azure Service Bus broker essentially goes to this poly retry capability. And what it essentially does, it has this method, it's called run operation. It returns a task. It returns a task because we are in the sort of IO-bound domain. For those who have attended Brendan's talk, he has probably talked about this as well, right? When we're sort of doing calls to over HTTP, over TCP/IP, database calls, we want to return a task because then we are essentially not blocking the thread. And then we're getting sort of this function with a time span of task, which is the actual operation. And then what this thing is actually doing, it sort of is a while loop, right? It checks whether the cancellation token is not canceled. It then sort of executes the actual operation, which is that function delegate. And if there was an exception, it sort of retries again. And if the server returns, hey, I'm currently busy, I'm doing back pressure for you because you're calling me too many times, right? Then sort of we do an await task delay. We wait a little bit until hopefully the server has had time to catch up, and then we're doing it again, right? So that's sort of this first piece of code that was there. And if we look at how this is going to be used, I have here a method. It was used this way. So for example, here, what we're seeing is that this retry policy run operation, it had sort of this, it was called this create message batch internal async within the curly braces. And as we can see on line 1 on the top, we have this message batch local variable, right? And then on line 4 and 5, between the curly braces on line 3 and 6, we essentially access the state, which is this local variable that is outside of the curly braces. And that state that is outside of the lambda. So that is a closure allocation. And how would we know that? Well, let's decompile the code, right? Let's see what's actually being lowered. And here I have this gibberish code that is sort of created by the compiler. And if we zoom in, we can see here there is this display class 16 allocation, and there is this new func of time span of task allocation that points to some sort of gibberish method somewhere, right? And we have here 2 allocations that are totally unnecessary that we can get rid of. And this is just because we're using a lambda that accesses state that is outside of the curly braces. And we can do that, and we have to do a little bit of sort of infrastructure library type of coding. So what we can do is we can create a new run operation method, and that run operation is going to use a value task. For those who haven't heard about value task is basically a discriminated union of a result and a yielding operation that is doing IO-bound stuff. When is that a helpful thing to use? Some people would argue always use a value task. Your mileage may vary. I'm usually applying it when I have cases where I know that, for example, in 8 or 9 out of 10 times, I'm actually getting a result, and I'm only yielding to do actual asynchronous work in only maybe 10% of the cases. That's when I use, for example, a value task, and I design it. So we were sort of using that because we said, well, we have actually also other methods that are returning a valid task, so we want to make sure that we're more performant and more modern. And so we do return a valid task of T result, and then what we're doing is we're sort of passing in a func of T1, time span and cancellation token that returns a valid task. And then on line 3, we're adding a T1 parameter. Why I'm using a generic? If we would be passing in the state that we want to pass to the lambda as an object, and if we would pass in an int, what then would happen, right? We would be boxing that int. So we want to use a generic that we're not boxing, because then we would create allocations for sort of value types, and we don't want to do that. And then what I'm doing is I'm simply calling this operation method, and I pass in T1 the state that is coming into that sort of delegate that was passed into this run operation method. And now when I have this in place, we can sort of do almost like functional programming, and we can start building on top of this library function something that doesn't return a result. How would we do that? Again, we return a value task. We need to get access to the state, and then we declare sort of a func of T1 again, but this time we're not doing valid task of T result. We're passing in the state from the outside, and then what we're doing is we can sort of leverage. C#9 has this nifty feature where you can declare static lambdas, right? So it's basically a compiler trick. What you can say is, when I have a lambda, you add the static thing, and then the compiler will ensure that you can only access state that is inside the lambda. So that means with this static async on line 6, we can only ever access state that is within the curly braces between line 7 and line 11, right? So we are sort of guaranteed by design that we never have a closure allocation. And then what we can do is, on line 12, we pass in a value tuple of sort of the state and the actual operation, and then inside the lambda, because we get access to the state, we sort of deconstruct that state into T1 and the actual operation by using sort of the value tuple deconstruction, and then we're calling this method. And then we're simply returning a default of object. And now we have sort of removed the closure allocation by adding this trick here. Cool. Now let's have a look how this actually looks like when we decompile it. And what we can see now is we have sort of the beloved pattern that I was already talking about, to say we're now in the safe zone. Because we can see now that we have this sort of 9__16_0 question mark and then equals pattern, right? And now we have sort of, we're pointing to a statically cached lambda, and now we have no longer allocations. So the 2 allocations that we got rid of, they're now, they're fully gone now. But how would you actually detect those allocations in your code, right? Because you don't want to decompile everything and look for that. So there are actually more proactive way how you can do this. So one way to do it is you can use a memory profiler, and you can watch out in your production code for excessive allocations of display class and various variants of action and function delegate allocations. That's one way to do it. I personally prefer to do it this way. So when you, for example, use JetBrains Rider, there is a heap allocation viewer plugin in Rider that you can use, and then it will tell you directly when you're writing your code that you have an allocation, a closure allocation. Then you can get rid of it. For those who are using Visual Studio, you can use the heap allocation analyzer plugin in Visual Studio, and it will tell you that you have a closure allocation. But then you might be thinking, but hey, Daniel, I don't have this problem in my code. I've never seen it. Why are you even talking about this? Well, for example, one sort of example that most people probably have is concurrent dictionary, right? Concurrent dictionary has a get or add method and an add or update method, where you have where you pass in a delegate. And when you, for example, in your add or update method or get or add method, when you're accessing state that is outside of the Lambda, and you do this on the hot path because you're trying to cache some stuff, right? Then you have closure allocations that will affect your runtime performance, right? But then maybe you're still skeptical and you're saying, but Daniel, come on, like all this sort of mental gymnastic to just get rid of 2 allocations, is that even worth it? I have an example here I work for a company called Particular Software, and we have a product that's called Service Bus and the whole platform around it, where we're doing sort of messaging type of middleware, where we sort of communicate with Azure Storage Queues, Azure Service Bus, SQS, SNS, and some other types of queuing system. And in there we have the pipeline execution engine, and the pipeline execution engine is basically the core of Service Bus that makes sure that we execute our customers' code as efficiently as possible, and it shouldn't be in the way. And I did their closure allocation optimizations to remove all sort of these closure allocations that were happening inside this sort of execution engine. And as you can see here on the screen, we actually, just by getting rid of all the closure allocations, we got a throughput improvement of 74 to 78%, which is massive, right? A 4x sort of throughput improvement by just getting rid of all closure allocations inside this sort of core infrastructure layer of Service Bus. And all the allocations are gone. So we went down from a whooping 20 megabyte of allocations to 1 byte of allocation, which is probably, I don't know, a rounding error, I don't know. But if you want to know more what I did there, you can go to goparticular.net/NDC-Porto-23-pipeline to read up. I wrote an entire blog post that talks about the optimizations that I did there. Okay, then the next one is pool and reuse buffers and larger objects under avoid excessive allocations. So one of the things that is happening, I already talked about this concept of lock tokens, and essentially whenever a message is received from Azure Service Bus, essentially this GUID comes over the network, right? Comes over TCP/IP, and I have this data segment, array segment on line 1, and what the code was doing inside sort of the SDK, it was taking this sort of byte stream, and then it was allocating. On line 3, it was allocating a buffer of 16 bytes, and then it was using buffer block copy to sort of take the array segment and copy all the byte arrays that were sort of on the network into that buffer, and then it was creating a GUID. And because it has to do, imagine you're using maybe Azure Service Bus and you're receiving thousands and thousands of messages a second from your production system. We're essentially allocating 16 bytes for every message that we're receiving, multiplied by the throughput that we're getting per second, right? So these allocations are essentially totally unnecessary. And at that time, I heard of this thing called array pool. Who has heard about the array pool in .NET? Few people. So array pool is basically, it's almost like a car rental, except you're not getting cars, you're getting arrays, right? So essentially when you want to have fun with your 6 friends, right, and you're saying, well, my car only fits like 4 people, you can go to the car rental and you can say, I want to have a car that fits at least 6 people into the car, right? And then you might getting a car that fits 8 people, but you can at least put 6 people into the car, then you're having fun with your friends, right? And then you, at the end of the day, you give back the car to the car rental. You might clean it or you might not clean it. That's extremely similar to the sort of the array pool. The array pool just gives you basically arrays. You can rent arrays instead of cars. And that was, I heard about that and was like, oh, cool. I can actually apply this trick because I know I have 16 bytes and I can optimize it. Let's use the array pool. So what I did is I introduced the array pool in the Azure SDK, and I rented an array for 16 bytes. As a quick reminder, when I'm saying 16 bytes, I'm not getting an array that fits exactly 60 bytes. I might get 24, 36, whatever. I'm getting sort of at least that I can fit 16 bytes into that array. And then we're doing buffer block copy, and at the end of the day, I have to return it. I have to sort of do array pool shared return. And I was like, cool, now I got rid of an allocation, 16 bytes on the hot path, multiplied by number of messages. I've done a great service to the Azure Service Bus team there, and I learned something about it. And that was the first time I was being able to apply the sort of the array pool stuff, right? I was pretty proud of myself. And I was like, oh, cool, let's have a look if it actually is faster. So I forced myself to write a test benchmark, and then sad trombone, as you can see here on the screen. Well, there is like, I actually got rid of all the allocations, but the problem is that even though I got rid of all the allocations, the code that I introduced was actually 226% slower than the original code. So now you might be asking yourself, well, is that a problem? Well, again, the context comes into play, right? Because we could say, if we are in a memory-constrained environment, we can actually say we achieved something because we got rid of memory allocations. So this might be an optimization where we're willing to trade off throughput against memory allocations. We might be saying, that's the thing we can do, right? But there is actually something we can apply that makes this code even faster. And we're going now to the next rule. So for small local buffers, consider using the stack. And I'm giving you here an example. So instead of using array pool to sort of rent an array, what you can do is with C# 7.3 and the introduction of span and memory and T, I'm going to talk a little bit about more about this a little bit later. You can actually use the stack collect keyword, and you can say, please allocate an array on the stack of the method. And one of the great things there is that when the method returns, that array is gone. So there is no garbage collection that has to happen there. So that's super efficient. And then what we can do is when we stack allocate that array, we can then use the asspan and copy-to method to sort of copy the bytes that we got from the network into sort of that memory, and then we can new up the GUID. Right? And then we actually got rid of all these sort of memory allocations. But some of you, I don't know, I'm always exposed to nerds and stuff like that. So some of you might be thinking, but Daniel, I actually went through the MSDN article and I know all the GUID constructor. And there is actually a GUID constructor that accepts a read-only span. Why are you even copying the memory? That's a really good question, because you should actually not copy the memory if you don't have to. I'm showing this here as sort of a demonstration because at the time when we were sort of writing these optimizations, the actual code that we actually wrote was way more complex. And there is another thing, but I feel it's a very good example to sort of show what you can do, but there is another thing with sort of GUIDs that, for example, you have to take into account. The byte representation of a GUID is actually in endianness. So depending on your system, it's either in big endian or in little endian. So it's in the network byte order or in the other order. And this code here, the original version that I showed you, is using buffer block copy. And buffer block copy actually takes care of endianness. So it always copies it in the right endianness of your sort of target system. But this version wouldn't do that, right? So again, it's a simplified version of the code, and the actual code that we wrote was way more complex. And some of the things that we had to trade off, because we were on net standard, we didn't have those GUID constructors that actually take a read-only span. And the team at that point felt like we need to copy the buffer, but then over time we actually learned that's actually nonsense. We don't have to do this. And then we did further iterations of the code. Okay? I just want to give you the full picture while still showing you a simple example. Hopefully that's clear. And I will talk a bit more about copying of memory and when you should not do that a little bit later. Let's measure this one. And as we can see, if we compare these different versions, here is the last version that is using for the smaller buffers, no longer the array pool, is now 45% faster, and also all the allocations are gone. Right? So we actually now achieved something, and we made the right trade-offs. And by the way, you might be thinking now, well, stack alloc, really cool, Daniel. Thank you very much for showing me this. I'm going to do this now everywhere, right? And there is things you should not be doing, because one of the things that a stack has, it has a certain sort of size limit, right? And you should, for example, never actually stack alloc unbounded stuff. So if stuff is out of your control, you should not do that. Luckily, we have now compiler warnings that actually are telling you, no, Daniel, don't do this. This is really stupid, right? When you're sitting in front of, when I'm sitting in front of the IDE. But for example, if you stack alloc more than a megabyte, as an example, right, things will go horribly wrong and things will explode in production, right? So be careful to not overdo this. Again, the context is quite important. So I have summarized here the rules under avoid excessive allocations to reduce the GC overhead. Think at least twice before using LINQ or unnecessary enumerations on the hot path. Be aware of closure allocations, pull and reuse buffers. For small and local buffers, consider using the stack. And there are two more things that I haven't talked about. Be aware of parameter overloads, where you, for example, have params arrays. This is always an allocation. Where possible and feasible, use value types, but pay attention to unnecessary boxing. We talked quickly about that. And whenever you can, move allocations away from the hot path where possible, right? Because, for example, if you have a byte array and you know you only have a single thread that is executing and accessing this byte array, but is sort of cycling, you can sort of, instead of doing it in the while loop, you can move it out of the while loop, right? And you can allocate one byte array, and then you can work with this byte array all the time, and you don't have an allocation anymore on the hot path, right? These are things that you can do to optimize your code. And let's go to the last one, which is to avoid unnecessary copying of memory. So with the introduction of sort of span and memory of T, and I'm giving you a very quick sort of introduction to span. So span is essentially just a pointer to a memory location, and that can be any sort of arbitrary memory, can be unmanaged memory or whatnot, right? And then you have a length to it. And I usually conceptualize it with almost like a curtain, right? So basically, if I have a chunk of memory like this, I basically have a pointer to somewhere in the memory, and then I pull in the curtain, which is the length, to essentially only see a specific slice. And then I'm guaranteed to only ever operate in that specific slice. So that's conceptually a span. I know it's a very highly simplified version of a span, and there are people that are giving talks about this topic, about span and memory of T and all these types of things that are hourly long, but I want to give you a quick introduction. And span is the one that is happening on the stack, and there is memory, right? And memory, you can only use, you cannot use span, or for example, on async methods. You have to use then memory of T. So that's sort of a really simplified version of span and memory of T. Let's have a look at the most important rules. And recently, David Fowler was tweeting about this. So the first, look for stream and byte array usages that are copied or manipulated without using span or memory. So apparently, according to David Fowler, using things like toArray as an example is still one of the on, for example, streams, is still one of the major sources of allocations on many .NET projects. So make sure that you're not doing that when you don't have to, or replace existing data manipulation methods with newer span or memory-based overloads. And the last example that I'm going to show you now in this talk will sort of bring all the rules that I've showed you together. And I'm going to talk about the EventHubs client. So EventHubs is sort of like Kafka. It's a streaming system where I sort of have topics that I can sort of send events to. And what it has, it also has a partitioning thing. And partitions, again, highly simplified, is basically almost like when you have a bookshelf, right? And you have sort of books with authors, and you're saying, well, I'm going to take all the books with the authors that start with letter A. I'm going to take them out of the bookshelf and put it into a box that has the letter A on it, right? And then I take the ones that are author with B and put it into a box with V. That's basically highly conceptualized. It's basically partitioning. And they also do that in this sort of EventHubs client. And their partition key algorithm that is used on 30 to 40% on the hot path that I had a look at. And I was looking at this piece of code, and this is how the code looked like. And sometimes allocations or things that slow down are very sort of hidden in the code. And you have to sort of develop a really good understanding of sort of the runtime, the BCL that you're using in order to spot it. But what we can see here is we have this method here in this partition key algorithm that basically says encoding get bytes. And get bytes already hints that, well, there will be a byte array that is going to be returned. And if you look at the method signature on line 11, we can see that a byte array is going to be passed into this partition key algorithm, right? And because .NET gives us an array, it cannot do any sort of buffer pooling, right? Because .NET doesn't know what kind of trickery we're going to do with that byte array, right? We might be assigning it to a static local field, or to a static field, or do whatever, right? And essentially, that's why it's sort of creating a new array and giving it back to us. And the problem of this code is the partition key algorithm is essentially depending on user input, right? So when you're using event hubs, you can set a partition key. For example, if you're using names of people, like I have Swiss German roots, I have already a pretty long name, right? So if you use my name, then it's gonna basically allocate as much memory as needed to sort of fill in my name, right? And if you add even more, if you add twice my name, it's going to allocate twice as much memory. If you put in a name that is shorter, it's going to allocate less memory. But we basically have variable size of memory that is going to be allocated in this piece of code, and that is something we want to get rid of. And what we can do is we can essentially bring everything together and then optimize this algorithm, this partition key algorithm. So the first thing we're going to apply is we're going to take the string, we're going to turn it into a span, because we want to use the span-based overloads to essentially make sure we're not sort of copying stuff where we don't need it, and we can arbitrarily slice the memory that we need to. And then once we have done that, what we are going to apply here is we're going to ask basically our encoding how large is that string. And maybe some people have heard about the get byte count. And get byte count is basically an exact length of a string. But we don't need that because we're going to apply another performance trick that I call overrenting. So what we're going to do is we're going to use get max byte count, and get max byte count is basically an approximation. It is just a simple math. It multiplies sort of the length here with encoding UTF-8 by 4, right? So it basically takes the length of string, multiplies it by 4, so it's a really fast operation. And then what we're going to do is we're essentially going to say, well, if the partition key is smaller than an arbitrary stack limit, and here I'm using 256 bytes, we're going to be in the things where we use for small and local buffers, use the stack, right? So what we're going to do is we're going to stack allocate. And for things that are bigger than that arbitrarily defined stack limit, we're going to use the array pool to actually rent the memory. And then we're going to call a method that essentially accepts the hash buffer that we just rented or stack allocated, and we pass it to that method. And now, because we sort of over-rented, right? Because if you remember, I said arbitrary stack limit 256, and I did stack allocate of 256. So if you have, for example, a string that actually only needs 16 bytes, we're still going to allocate 256 bytes. And I'm going to talk about why that's actually better than actually allocate the exact amount of memory a little bit later. But then what we're going to do is we call this method, and it will fill in the bytes into the hash buffer, and it will tell us how much byte it has actually written, right? It gives us that back, and now we can basically bring in the curtain, right? Because we know that it's 256 as an example with the 16 bytes, right? But it will tell us, I only wrote 16 bytes into your hash buffer that you gave me, right? And now we can pull in the curtain and say, we slice it on line 19 from basically the start point to the 16 bytes, right? And now we are safe. And then we give this sort of read-only span to the method. And then what we have to do is, when we are in the cases where we actually sort of rented the buffer, then we can have to return it again. And maybe you're saying, but why are you not using a try finally? Are you nuts? Well, we actually looked at, because we're on a high performance sort of code where, because we're executing on 30 to 40% on the hot path, this partition key algorithm, we were thinking about sort of the boundary conditions of when can this code actually go wrong, and we couldn't come up with a thing where we said, well, it's probably not going to go wrong. We might be wrong, but we will see, right? So we said we're going to avoid the try finally to sort of not blow up sort of the method stack size, because again, we're high performant, and the method stack size actually is also relevant, how large the method is in high performance systems. So we essentially avoided the try final in this specific case. Okay, and then we pass in the read-only span to this compute hash method, and the rest is exactly the same. And now I told you about this overrenting thing. So there is actually a trick that you can apply. In cases, so because .NET wants to be safe by default, when you stack allocate, it gives you always sort of clean memory. Right? There will never be any garbage in there. And if you stack allocate 256 bytes, it will basically go and say, oh, that person needs memory of 260 bytes. Let's give that person a clean memory array. So if there was stuff in there, in that memory that you're trying to stack allocate, it's going to clear 256 positions for you so that you're getting all zeros, basically, right? And you can say, well, I'm smart, I know what I'm doing, or maybe I'm just crazy. And then you can add on line 1, you can see up there, the skips locals init attribute. And then you're basically telling the compiler, don't emit sort of that code that clears the memory. And you might think, well, why would you ever do that? Well, I told you, right, that we are in exact control of this code and we know exactly how much bytes we're going to write. So, and we're then pulling in the curtain. So even if there is garbage in this 256 bytes, right, because we only wrote 16 bytes, we're never going to see this garbage that is in there. So we don't care about the rest being all zeros or arbitrary bytes. So we can basically optimize it. And then this code becomes faster than actually getting exact lengths and stack allocating the exact number of bytes. So that's a trickery that you can do as well. Let's measure it. And what we can see here is the before and after executed against multiple string sizes. And again, when you're doing benchmarks, right, you also have to think about what are the boundary conditions of my code. And because I have stack allocated memory on the 256, I also want to benchmark things that are around sort of the 256 byte string length, byte length area, and also things that is higher, right? So I have basically permutations of things where I execute this benchmark, and overall what we can see is the new code is now 38 to 74% faster, and all the allocations are gone, right? So previously we were basically depending on the input and had sort of arbitrary allocations happening, right? And now this is no longer here because we have stack allocated and we're doing buffer rental and everything like that, and it's also way faster. Okay, I'm going to summarize the rules that we looked at. Look for stream and byte usages that are copied and manipulated without using span or memory. Replace existing data manipulation methods with newer span or memory-based variants. And the last one, watch out for immutable read-only data that is copied. Whenever you have data that is immutable or read-only, you don't have to copy it, right? Because it's by design not going to be modified. You might be laughing, but I have seen code even in the Azure .NET SDK where this happened, right? And then you can just, for free, you can get less allocations by not doing that. Okay, here I have also summarized, for those who haven't had a chance to sort of make a picture, all the avoid excessive allocation rules. I have it here on the slides. Should you wish to take a picture, and you might also get it in the recording, but I want to show it here sort of for completeness reason. And the last one that I've already showed here as well, avoid unnecessary copying of memory here on the screen. And because I want to use the time quickly to give you a little challenge because it's almost the end of the day. So in case you're up for a challenge, you can reach out to me over Twitter, LinkedIn, or whatever. And because what happened was when I optimized this code, what actually happened was the original version of the compute hash method had a bug in it. Can you spot it? This is the algorithm that I'm showing here on the code. If you're up for this challenge, take a picture, think about it, and shout it out to me. You can also reach out in the hallways if you want, if you're up for that challenge, and let me know what bug was in there. Luckily, we discovered the bug before we shipped that version, so it's actually not shipped in the Azure SDK because it was failing on some environments. And in some environments it was successfully passing. And I'm giving you a hint. Think about what is the most important characteristics of a hashing function. And think about, can this be guaranteed with this type of code or not, and especially with the optimizations. Let me wrap it up. So again, at scale implementation details matter. Again, I don't want you to go back to your projects and apply all these types of optimizations everywhere, right? First of all, if you have expensive database calls, HTTP calls, right, IO-bound stuff, tweak those first, because you're getting tens or hundreds of sort of orders of magnitude more throughput improvement in your production system when you optimize your database calls, your entity framework, lazy loading, and all that type of stuff first, right? Only if you have optimized that and you understand sort of the ramifications of these things, then think about potentially on the hop path applying the things, the tips and tricks that I have shown you here today, because then you can combine these things together and you get like a really, really high throughput system out of it. And in all other cases, don't even bother, right? Okay? And just to sort of summarize it, in the Event Hubs case, all the optimizations that I contributed to Event Hubs ended up sort of in real production scenarios, increasing the throughput by 8% on sort of the publishing throughput, and to 3 to 4% on the sort of incoming path. And as you can imagine, if you have a system that pumps 20 megabytes sort of per partition or whatever data through, and you're getting, just by upgrading the Azure service, the Event Hubs SDK to the next version, you're getting 8% more throughput improvement, or 3 to 4% throughput. You're actually getting more value out of the library for the money that you're paying Microsoft, right? So that's pretty cool. And who wouldn't want to have an 8% faster car just for free, right? Except I'm only allowed to drive a Kia Ceed because I lost the conversation with my wife to get a faster car. But anyway, I'm digressing. So again, it truly matters for me. Think about the context of the code. Apply these principles that I showed you where it matters. In all other cases, potentially favor readability, and just use whatever version that you feel most comfortable with, and don't even bother about the optimization that I showed you today. In all the other cases, do apply those. For those who want to sort of get more details about the code, the examples, I have a full README on github.com/DanielMarbach/performance tricks Azure SDK. It's also in the sort of code up there. And here on the bottom, I also have a QR code. Should you wish to sort of get sort of my expertise on your message-based system, you can also sort of make a screenshot of this code, and then you can reach out to me, and I'll help you gladly to make your message-based system faster, and for sort of a free consulting if you want that. But that's all from my end. Happy coding for all of you, and if you have any questions, feel free to quickly ask a question. I just saw I'm in the interest of time. I think I'm already on the time boundary, so I guess you can come to me and ask me questions directly.